let's take a look at 7.2 on the natural logarithm and how it's defined in calculus. So first we're going to define f of x. So we're going to suppose f of x is equal to 1 over x for x greater than 0. Then we're going to define, and then so that function, 1 over x greater than 0, we know it looks like this. I did this earlier. Looks about like this. And approaches those asymptotes. Well, that was weird. Like this. Oops. Here's the y-axis. Here's the x-axis. And we can make those look like that. A little better. You get the idea. You know what that looks like. So it's asymptotic, of course. So that's our function 1 over x. So then we're going to define ln x to equal the integral from 1 to x of 1 over t dt for x greater than 0. Seems kind of weird at first, but it allows us to define everything about logarithms that we already know. So everything will be in terms of the natural log. I'll move this over a little bit for us. The number e, so this, we would go from 1, so 1 would be about here because it's symmetric, right? So 1 would be here, and then x would be here, wherever x is, like that. And so when you are calculating that, that's basically area. That's area in this region. Like that. So the number e is that number that you basically have area 1. So the number e is the real number such that ln e is equal to, so that'd be the integral from 1 to e of 1 over t dt that equals 1. So wherever that is, that's the number e. So it's the area. So that's area from 1 to e is 1. And so we know what that is, right? That's 2.71828. Let me look that up. Drawing a blank. Usually I know those all by heart real easily. But today I'm not thinking of it. That's it. I had it right. 2.7182818284595. But that's not the point. The point is that it's a real number, and it is transcendental. It's not a root of a polynomial or anything with real coefficients. So with that definition, we get all the properties of the natural logarithm. That's what's kind of cool about it. So with that definition, we get those properties. Let's take a look at them. So here's the properties. of ln x. So we will let a and b be greater than 0. And n is rational. That'll be a power, but it doesn't really matter, but that's how they define it in the book. So 1, here's all the properties. ln 1 is equal to 0. 2, ln AB is equal to ln A plus ln B. 3, ln A to the n is equal to n times ln A. And 4, ln A over B is equal to ln A minus ln B. So those are all the properties of logarithms that you would know, you know and love. So we can prove those using all the properties, using this definition and the properties of integration. So we won't look at all of them. Let's look at the proof of a couple of these. So number one is ln 1. So we know ln x is equal to the integral of 1 to x, 1 over t dt. So we're going to just say integral of 1 to 1 of 1 over t dt. Well, that's just ln 1 minus ln 1, which is equal to 0. I mean, that's it. You subtract the same thing, you get 0. So you evaluate at 1, you get 0. That's what we would say. There's no area, essentially. Okay. 2, let's do 2. 2 is basically the, what am I doing on 2? Okay. Two is a little more difficult. Okay, I was going to say it has some work to do. Okay, so let's do 2. So what we look then at is take the derivative dx of ln x. That's dx of integral from 1 to x, 1 over t dt. Well, that'll just be 1 over x. So if we look at d dx of ln A plus ln x, that's equal to, the variable is x, so the derivative of ln A, if A is fixed, is 0. So it's 0 plus 1 over x, which is, of course, just 1 over x. So, therefore, ln AX and ln A plus ln x differ only by A only by a constant C. So ln AX is equal to ln A plus ln x plus C. now solve for c, and then we choose x to equal 1. So you get ln A is equal to ln A plus ln 1 plus c. So you get ln A is equal to ln A plus c if and only if c is equal to 0. So you get this expansion is true for any x and a. Okay, let's do properties of derivatives. So the rest of those you can look up. I think they do the rest in the book. Let's go ahead and do properties of derivatives. So moving along. So properties of derivatives. Of the natural log function. So we kind of already looked at one of them. So if you do d dx of ln x, that's equal to 1 over x, provided that x is positive. Then if you want to use chain rule, you get d dx of ln u. That, of course, is just 1 over u times u prime, provided that u is positive. Then you can look at d dx of ln absolute value of u. That'll equal to 1 over u times u prime. And in that case, your u is just non-zero. And that's all right. That's all coming right from the definition, all right from here. So when you do the derivative of this, you're getting, that's the form you're getting, because you do this derivative and you're using the fundamental theorem of calculus to simplify and get just 1 over x. Excuse me. Okay, let's look at some examples. So let's suppose f of x is equal to ln x squared plus 1. So when you do that derivative, you just get 1 over and then do the chain rule. So if you look at the derivative of f prime of x, that ends up being 1 over x squared plus 1 times that derivative of the bottom, which is just 2x. So you normally write that as 2x over x squared plus 1. Note here that x squared plus 1 is always positive. They often just kind of ignore that. I have to say, they're not real careful about that being positive. So this next example, for example, is assumed it has to be positive, but I'll show you the next one. So let's look at this example. So if you have g of x equal to ln times the square root of x plus 1. Let's go ahead and write that then as ln x plus 1 to the half power. And properties of logarithms allow us to bring that out front. So you end up with just that. So you can do that. That is a property, just like you know a logarithm. So now when you do that derivative, the half just tags along. So, what I was going to mention here is it's basically assumed that x plus 1 has to be positive or non-negative in this case. and essentially positive because you won't be able to divide by something that's 0 anyway. So try the derivative. Okay, so see what you get. So g prime of x is equal to what? Well, it's the half, just tags along, but I'll write that as 1 over your x plus 1 to the half. And then here's your half somewhere. And then times that derivative. So you end up having, actually, let me fix this. Let's try that again. My notes look messed up. Okay, so you have a half, and then it's times 1 over x plus 1. Excuse me. And then it's just well, yeah, that's it. So it's just that. So it's times, and then derivative of that is just 1. So that's really just 1 over, it's rather simple actually, 2 times x plus 1. So there's, oh, that's right. I was going to show you 2 ways of doing it. Oh, let's see what I was doing. So if you just kept this in here, you get 1 over that, and then its derivative brings it down and it simplifies. So let's just do it. This was b. So we just did the b method. What I wanted to show you was if you did not simplify it, it should be the same, of course. So if you did the first method and you did g prime of x, it would be 1 over the x plus 1 to the half, and then times that derivative would be a half times x plus 1 to the negative a half, which brings it back down. And then when you multiply those, you get the same thing. So this and this is the same thing, whether you simplify ahead of time or not. So anyway, that's why I was showing you 2 different methods. I didn't realize that at first. Okay, let's see. We got 2 more to go for this section. Oh no, we got a few more things to do. Okay, we got a bit to do. Okay, let's do 1 more and then I'll do another video. Okay, so next one, this is simplifying a lot first. So let's do this guy. Okay, suppose you have y equal to ln cube root of x squared minus 1 over x squared plus 1. So you don't want to just start taking derivatives. That'd be ridiculous. So simplify that a little bit first. Let's bring down the 1/3. And then it's going to be times ln of what's inside. And we're going to subtract those. So now you're just going to get 1 over and 1 over, and you're good to go. So now do the derivative of that. Y prime. What is that going to be? Derivatives are really easy, and then a little algebra to simplify is what I end up doing. Oh, one of them is negative, huh? This one's negative. Let's fix that. There, that's better. So yeah, you get 1/3. It just stays. And let's do the derivative of that. So it's 1 over x squared minus 1. That's how you do it. You'll get used to this. And then times that derivative. So that's just 2x on top using the chain rule. Minus, and then same thing, you get 2x on top again, but it's just the plus x squared plus 1. Now that is it. That's the derivative, but normally they'll want you to write that as one fraction so that you can set numerators or denominators equal to 0 and solve. So normally you want to simplify that. So you get 1/3, and then you get 2x times x squared plus 1 minus 2x times x squared minus 1 all over the common denominator, which is x squared minus 1, x squared plus 1, which looks like a difference of squares, doesn't it? Okay, simplify the top. So we get 1/3, and then the top. And I'll distribute and simplify a little bit, I think. No, it doesn't matter. So you get 2x cubed plus 2x minus 2x cubed plus 2x all over x squared minus 1, x squared plus 1. Oh, excuse me. So that simplifies. Those are gone. So that one and that one are gone. So you get just 4x. So you get a 4x over... Oh, didn't do it. 3, bring the 3 down now, and then that's just x squared minus 1, x squared plus 1. And you could write that as x to the 4th minus 1 if you wanted to, but not really a big deal there. But that's typical. You don't really want to leave it in this form after you take a derivative because you don't know when it's 0. You want to simplify it so you can see when denominators are 0 and numerators are 0. Because remember, we are concerned when x is equal to 0, that's a critical value. And then x equal to plus or minus 1 are more critical values where denominator is 0. So factoring and, combining the rational expression is important when you're doing this kind of stuff. Okay, next we will go on to implicit differentiation with logarithms. And yeah, we got a few more things to do here. So one more video for this section.